In this video, I will present PAC-Learning, a concept invented in 1984 by Leslie Valiant, which has gained much interest lately with the rise of machine learning. PAC-Learning is arguably one of the main tools to analyze the theoretical properties of machine learning algorithms. Basically, the question that was asked is the following: how much data is needed for a machine learning algorithm to have learned? But before going further, let's be more precise about the setting. Basically, we have a bunch of data, and each data has features along with a label, and we want to predict the labels from the features. So a prediction function will be a map from the features to the labels. It is common in PAC-Learning, at least for now, for this video, to assume that there is some underlying deterministic real prediction function which is unknown to us, and the goal of machine learning is to compute such a map. To do so, we are given a sample of data, that is a set of pairs of features and values. So a machine learning algorithm is actually a map from the set of samples to the set of prediction functions. It turns out that this very basic setting has a huge amount of applications. Well, I don't think I need to tell you the importance of machine learning these days. Now, let's get back to the fundamental question we raised. Evidently, the trouble with the question is that it is poorly phrased. There are actually two major underlying problems with it. The first trouble is what is meant by have learned. Valiant argued that one might measure the knowledge of an algorithm by how often it is able to make the right prediction. However, we now have this notion of how often that we need to be more precise about. One way to formalize it is to assume that there is some probability distribution over the set of data. For instance, if you want to predict the title of a newspaper article from its main picture, you need to consider a probability distribution on newspaper articles in general. But note that this probability distribution may then differ from one data set to another, as the articles from the New York Times may not have the same kind of main picture patterns as the articles from an English tabloid like The Sun. We'll get back to this issue at the end of this video. In any case, we assume a probability distribution over data. We can now measure how good a prediction function is by measuring how often it predicts the right value of a feature drawn according to this probability distribution. So a prediction function is said to be epsilon approximately correct if it yields accurate prediction with probability at least 1 minus epsilon. In other words, an epsilon approximately correct is highly likely to be correct. Now we want to say that a machine learning algorithm is epsilon approximately correct if it computes an epsilon approximately correct prediction function. That makes sense, right? However, here the trouble is that the prediction function computed by the machine learning algorithm depends on the data set, which should be drawn randomly. So we need to take into account the randomness of the sample set as well. Evidently, there will always be bad sample sets that do not allow for any efficient learning. Valiant was interested in how unlikely those bad sample sets are. In particular, he was happy enough with machine learning algorithms for which bad sample sets are highly unlikely, i.e. occur with probability smaller than some delta. Now, this seems like it will be the case if the sample sets are large enough. If the sample sets are large enough, it's unlikely to get a bad one intuitively. Well, Valiant's question is precisely that. How large does a sample set need to be in order to guarantee that with high probability, our machine learning algorithm will compute an epsilon approximately correct prediction function? Spoiler alert, if this sample set needs to be exponentially large, our quest for a correct prediction function can be regarded as hopeless, at least using that machine learning algorithm. This leads us to the following definition. A machine learning algorithm will be said to be PAC-Learning if the number n of data in the sample set required to compute with probability 1 minus delta prediction function that is epsilon approximately correct is polynomial in 1 over delta and 1 over epsilon. More precisely, a machine learning algorithm, MLA, is PAC-Learning if there exists some polynomial of two variable p, such that for any epsilon and delta positive, and for all sizes n of the sample set that is greater than the polynomial in 1 over delta and 1 over epsilon, we have that the probability when we draw the sample set Sn of size n, the probability when we draw that the prediction function computed by our machine learning algorithm is epsilon correct. If this probability is at least 1 minus delta, we say that our machine learning algorithm is PAC-Learning. This is really saying that the machine learning algorithm computes epsilon correct prediction functions with high probability on polynomially sized sample sets. Let me now take this one step further by writing the definition of the computed prediction function being epsilon correct. This leads us to the condition that with probability at least 1 minus delta for sample sets, the probability that a prediction made using our machine learning algorithm matches the real label for some data drawn randomly is at least 1 minus epsilon. So it's a bit of a tricky writing here, it's a bit of a tricky way of noting things, and it does take some time to get used to, but this is really a wonderful definition. Now I should say that in some definitions of PAC-Learning, you don't have the concept of polynomial amount of data. It could be just that we require the sample size to be a function of epsilon and delta, which needs not be a polynomial in 1 over epsilon and 1 over delta. So you should be a bit careful when you read about PAC-Learning. It could have slightly different meaning depending on resources. But in any case, for the purpose of many theorems, most importantly the fundamental theorem of statistics, the fact that the sample set is polynomial in size as a function of 1 over epsilon and 1 over delta does not really matter. Indeed, in future videos we're going to see that the concept of VC dimension determines the PAC-learnability of a problem, and we'll see that if the VC dimension is finite, then the problem is PAC-learnable with a polynomial amount of data, and if the VC dimension is infinite, then the problem is not PAC-learnable, even with a non-polynomial size of data. So I hope you've sort of grasped some of the main ideas behind this PAC-Learning concept. There are two things I now need to add. A big assumption here behind the data set, actually two big assumptions. The first one is that it is a product distribution, that is, we assume that the data of the sample sets are drawn IID, independently and identically distributed according to some distribution. And the second thing that we assume is that this distribution that the data of the sample set are drawn from is the same as the probability distribution that we use to judge the quality of our prediction function. So it's the same as the distribution that X here is drawn from. This may not be adequate in practice. It might be that a lot of the data that we collect are like easy to collect data. And if the data that we collect are easy to collect, they may not correspond to the actual distribution of the data that we are really interested in practice and that we should be using to judge the quality of a prediction function. The last remark I want to make is that usually we don't talk about the PAC-learning property of an algorithm, but rather we talk about the PAC-learnability of a problem. And so a problem is said to be PAC-learnable if there exists a machine learning algorithm that is PAC-learning for the machine learning problem that we have to deal with. And you see that in this setting, the definition of PAC-learnability really depends on, one, the set of features that we are considering and the set of labels we are considering. Two, the underlying prediction function. Some underlying prediction function may be easier to compute through a machine learning algorithm than others. And three, PAC-learnability depends on the probability distribution that we consider. In particular, for instance, if a probability distribution that is a Dirac that has all its weights on one option is always going to be PAC-learnable. And one last remark I need to make is that there are generalizations as well of PAC-learning to more general setting, because actually the setting of interest here is very restrictive. So for one thing, the prediction function may not be an actual function usually, it may be stochastic. For some features, we may have different kinds of observations. There's a generalization of PAC-learning for this. And another thing is that it might be impossible to do the right predictions, like the set of prediction function we may be interested in may not contain the right one, the real fundamental prediction function that we are trying to compute. And especially to avoid overfitting, it can be very useful in practice to consider very relatively small sets of prediction functions that we are searching an element from. And in such a case, we may not be able to get the right prediction function, but we may be happy enough with sort of the best prediction function that is in our set of prediction functions that we want to be taking our prediction function from. And in such a case, there are still a relevant notion of PAC-Learning, which is called agnostic PAC-Learning. And I will be making a future video on agnostic PAC-Learning.